Number 13, the integral from 0 to infinity, x squared plus 10 over 3x to the fifth plus 6x plus 10 dx. This is improper because the upper limit's infinite. We're fine with this lower limit of 0. We're not going to be dividing by 0. There's no domain restriction. But okay, so let's have our intuition. As x approaches infinity, our function, this rational function, is going to behave very similarly to x squared over 3x to the fifth. You can imagine as x keeps growing, like x becomes 10 billion, 10 billion squared plus 10, who cares about that plus 10? It's really insignificant. Similarly, 10 billion to the fifth power, who cares about 10 billion and another 10? We're fifth powering 10 billion. That's going to be so much bigger. So these two terms become insignificant, okay? So that's why this guy will behave very similarly to this guy over here, which we can simplify to 1 over 3x cubed. Therefore, our integral is likely going to converge because from our intuition, this function that behaves very similarly to converges, okay? Now, we want to set up a comparison test here because we probably don't want to evaluate directly this integral. So what can we compare it to? Well, we technically, in this case, could directly compare it with 1 over x cubed dx. But good luck showing that, that this guy is actually bigger than our guy. It's kind of hard to show. You could obviously just write the inequality and maybe you'll get away with it. But probably your grader or instructor wants you to show a little bit more evidence that 1 over x cubed is bigger than this guy. And if you're not allowed a calculator or a graphing calculator or something like that, it's hard. But let's double check real quick that it's the case actually. So Desmos. So you can see that from looks like around 1 or even before that, I guess, we're interested in, well, our improper integral is from 0 all the way to infinity, okay? So we know that this guy, 1 over x cubed, this one up here, is bigger than our function that we want. If we keep going, it's going to always be bigger, okay? We can zoom in if we want. I'm not going to do that, but we see that it's bigger. And then, however, this part over here is also improper. So we would have to compare it to, like, for example, 1 to infinity. And then we know that 0 to 1, this portion over here is finite. So that's not an issue at all, okay? So if we're able to show algebraically that 1 over x cubed is bigger than our function, we can use it, okay? Again, it just depends how picky your instructor or grader is. If you have to actually have a convincing argument without just stating it, then it's kind of hard to show that. So this is what I did instead. Okay, so I did break it up from 0 to infinity. I mean, it's from 0 to 1, 1 to infinity. Okay? Because this guy, as I said earlier, is finite. It's not an improper integral at all. So it's going to be some value by the fundamental theorem of calculus. This part's still improper though, so I'm going to do a comparison for this one. We can make this comparison actually. Our function is less than or equal to x squared plus 10 over 3x to the fifth. How did I get this? Well, the numerator is the same. You can see the denominator, I got rid of these two other terms here. So our denominator is going to be smaller on this right-hand side, right? Therefore, our value after we do the division is going to be bigger. We're dividing by less. Okay? This is a clear comparison versus you just write less than or equal to 1 over x cubed. It's not as clear. Okay? Now, this improper integral from 1 to infinity of x squared plus 10 over 3x to the fifth dx, I can just use some algebra to split it up into these two over here. Split up the fraction. Okay. And then the next step I just simplified. So the first integral became 1 over 3x cubed dx. The second integral became 10 over 3x to the fifth dx. We know both of these converge because the power of x at the bottom is bigger than 1. If it's bigger than 1, it converges. Okay, so both integrals converge. Therefore, by the comparison test, to be more precise, by the comparison test, this guy converges, and now both guys converge and are finite, so our original guy converges as well. Okay, so let me just scroll down to this portion over here to show it again. Okay, the point I want to make is, once more, it's hard to algebraically show, in my opinion at least, that our function is less than or equal to 1 over x cubed, the guy we had intuition about. So instead, I just chose something very similar to our function. I just got rid of these two bottom terms, and this is much more clear to most people, hopefully, that our guy over here on the right-hand side is bigger because we're dividing by less. Okay, and then this integral was it's easy as well to determine the convergence of. And then by comparison test, our guy converges as well. Okay, so this just goes to show that our intuition is correct, but sometimes we want to pick something a little different. It was really similar, technically, if you think about it. If we use that intuition again on this guy over here, it'll still be like the 1 over x cubed type of function, right? But it's hard to show the comparison. So just pick something that's easy to show the comparison, that's also easy to evaluate or determine the convergence of, is the moral that I want to, not the moral, the lesson that I want to impart in this video.